similar, but there's something that's different. So an isomer has many different types. First, I'm going to give you the overview, and then we'll look at each different type of isomer that we could have. So isomers will always have the same chemical formula, but they're going to have a different arrangement of atoms. So the atoms will the same atoms will be there, and the same number of atoms will be there, but they'll be bonded differently, or they'll be arranged differently. Bonded or arranged. So structural is one of these branches. Isomers either come as structural isomers, or they come as stereoisomers. The structural isomers are the easiest ones to see. It's when you have different bonds present, or different bonding present. So let's say that we had a molecule that was made of A, B. Okay, so an isomer of that would be if we had A, B, A. So you have two A's in both. The bonding is different though, because you can tell we have A bonded to A in this case, but there's no A bonded to A in this case. I like to follow through just to see if I have the same type of bonding, especially when they're a little more complicated than that. So structural, same atoms present, but there's different bonding present. Stereoisomers are going to have the same bonding, but they're going to have a different spatial arrangement. And there's two different types of stereoisomers. Stereoisomers are either going to be geometric, and geometric isomers are not mirror images of each other, or they're going to be optical. Optical isomers are non-superimposable mirror images. So real quick, a geometric isomer would be like these guys. So I can see that they're not mirror images of each other. This is not the mirror image of that. They look different. I can see that. But I do have the same bonding, because up top I've got a red, both of them have a red bonded to a black and a white bonded to the same black. And on the other side, I've got a red bonded to a black and a white bonded to a black. So they can't be structural. They have the same bonds present, but they're clearly different because they don't look the same. Okay, so those are geometric. They're non-mirror images. The other type is optical. Optical are non-superimposable mirror images. So like your hands are optical isomers, and they're optical because these guys are mirror images of each other. If I put my hand up to a mirror, it looks just like that, but you can't superimpose, meaning if I lost my left hand and duplicated my right and stuck it over here, there would be a difference. I'll never be able to stick my right hand exactly into my left hand because of these guys. Or I would have the back of a hand where I should have a palm. So they're clearly different, even though they're mirror images of each other. So I still have the same bonding. I've got a palm that's connected to, you know, a pinky, a ring, a middle, and an index. Like, I've got the same bonding, so it's not a structural, but they're mirror images of each other. So that's the optical. Let's look a little more in depth at structural. So structural isomers, what you want to do is you want to see if you have the same bonding, so it's good to trace atom by atom to check and see. Make sure you have the correct formula. Quite often, students will be asked to draw structural isomers and they'll throw in an extra H. Well, it's now a different molecule. Another thing you want to try to remember, and this one's hard, this one requires maybe playing with model kits to get a handle of it, is single bonds can rotate. For example, here's a molecule. This single bond can rotate. So I could have this pointing up or down, and it's the same molecule. You know, I didn't break any bonds to do that. Single bonds are kind of like, I can rotate. I'm still me. So let's see which of these, I've got 5 drawings, are isomers of C3H8O. So I didn't draw in any of the H's, but if you have these little sticks, those are going to be our H's. So I can see that all of them have 3 carbons. All of them have 1 oxygen. And then real quick, I'll make sure that I did put on 8 H's for each one. So I actually drew 1 H. Yeah, okay. So they all have the same formula. Let's see if they're different molecules, or if they're the same molecule. So for this first one, I'm going to compare this guy to this guy. I have an oxygen bonded to a carbon in both, but then that carbon is bonded to 1 carbon in this molecule, and the carbon is bonded to 2 carbons in this molecule. So clearly, a bond would have to be broken and then reattached to turn this into this. So the same atoms are present, but they're different isomers. So I one isomer here. I have a second one here. Let's see if there's any others. So I'll look at this guy, and this one's pretty easy to see because here I've got 3 carbons in a row. This doesn't have 3 carbons in a row. So I can see that this clearly is different from that. You can't just rotate bonds and turn this into this. You know, so I could say I've got an oxygen bonded to a carbon, I've got an oxygen bonded to 2 carbons. They're different. So this is a 3rd isomer. Then we look at this guy. I've got, let's see, now I've got to compare it to all of these. I can see it's different from this very easily. It looks awfully similar to this one, so I want to see if it is. I've got an oxygen bonded to an H, bonded to an H, yep. Bonded to a carbon that's bonded to 2 other carbons. Yep, they're the same. So this molecule is that molecule. It's just different because this one bent a little bit. So it'd be like, let's see, I don't know if I can make shape. So here, let's see, like you can just see that this guy bent up, and then it rotated a little bit. So that's it. It's the same molecule. And I can look at it this way. Let me put this, whoops. Let's see. So here, I can see that I've got, you can see this, carbon attached to carbon attached to carbon, and the middle carbon bonded to an oxygen. Yeah, that matches that. And then to turn it into this thing, I just have to rotate it. Oh, okay, so same thing. All right, and then let's see if this matches any of them. It looks suspiciously similar to that one, and you can see it really, it's just rotated around. That's all that is. So this is going to be the same as that one. This one's kind of, yeah, it's kind of funny. It's almost like, you know, who am I? I'm Ms. Kaufman. Who am I now? I'm still Ms. Kaufman. So these are the same. Not a new thing. This is the same as that. Not a new thing. So I have 3 different isomers for that. And notice, isomers don't have to be the same thing. So if you were given this guy as your original isomer, if you know your functional groups already, you'll see COH, and you'll know that's alcohol. So this is an alcohol. This also has COH. That's an alcohol. This is not. This has COC. This is an ether. So structural isomers can make different compounds. So you can have an acid that will be a structural isomer of an ester, for example. So very different things. One smells sweet, one's acidic. Stereoisomers. So the stereoisomers have 2 types. We have geometric and we have optical. Geometric is where they are not mirror images. So here's one isomer of this guy. You can see that it's not a mirror image. If I imagined this is a mirror, this would not reflect that. You'd have an F up here, right? An F and an F there. So if the things are on the same side, like these H's are both on the top of this double bond, cis is for same. So this is the cis isomer of this guy. And if they go across diagonally, like transcontinental, they're going across, this is trans. So these are the cis and trans isomers. It's a type of geometric isomer. So the same bonding's there because I can see they're not structural isomers. I've got a carbon bonded to a hydrogen and a fluorine. I've got a carbon bonded to a hydrogen and a fluorine, double bonded to a carbon, bonded to a hydrogen, and bonded to a fluorine. Yep. Same connectivity, so they're not structural isomers, but they clearly look different. And they are, and these guys behave differently too. For example, if the things are on the same side, then maybe those can both reach something as in reaching, you know, a strand of DNA. Cisplatin is a drug where the cis version is a cancer-fighting drug, and the trans version does nothing. So cis and trans gives different properties. The last type of isomer, so it's the second type of stereoisomer, is optical. So optical isomers are the non-superimposable mirror images. Looks the same, not the same. Look for 4 different things attached to one atom to figure out if you have an optical isomer. So with this guy, I can see got green matching up with green, red with red, white with white, and then there's purple on the opposite. So they look exactly the same, but no matter what I do, I'm not going to be able to superimpose these guys. So right now I've got the purple, white in the middle lined up, but these are different. So if I match these, maybe I'll go like that. Well, now I've got white sticking down, white up. That's not going to work. So no matter what I do, I'm not going to get these guys to line up because these guys are optical isomers, mirror images, but non-superimposable. So look for 4 different things and then see if they're attached in the same direction. And that's kind of hard. Sometimes that one's going to take practice. You might want to build them and actually see. If you are asked to draw one of these guys, then you have your original. You have to draw them in 3D. If you don't draw them in 3D, nobody can tell if it's an optical isomer of itself. So, or if it's just the same molecule. So here's my mirror. So this plane is going to reflect on this side and this side. So if I were asked to draw the isomer of this, the optical isomer of this guy, what I would do is I'm going to go ahead and have this central thing bonded straight up to something, and then it's going to have a line going back. That's why it's dashed and fading down, and then a line that's just coming straight that way, and then a line that's coming out at us, like 3D, woo, it's coming straight out, and it's going to go like that. So I just made those the exact opposite, right? And then I'm going to say, well, the purple is coming this way, and the green is going away from the plane of the board. That's the dashed line, so that's green. This was green also. White, it's not really very white. I don't have a white marker. And then I can see red is going away. So now I've drawn 2 optical isomers, non-superimposable. And let's see. So this guy is going to be this one. Right? No, it's going to be this guy. So let's see. Yeah, that's going to be as good as it gets. So this guy is going back. This is coming towards us. Purple in the plane. And then for this one, I have like that. The green's going back that way. The red's coming out at us. And then the white's going up. And that's it. So, yep. Okay, and they're called optical isomers because they're optically active, which means if you have a plane of light, so you have like this thin slit that light is going to pass through. Ooh, there's a little slit made of plane. A slit of light would hit these molecules, and this molecule would rotate the light one way. This would rotate it another way. So they're optically active because they rotate light in a different way. Isomers.
Tom Danielson.